Greetings, parasite ecologists. In the past few videos, we've been talking about how nematodes can teach us about the fundamental principles of parasite ecology. We've already discussed how nematodes are a selective pressure that pushes their hosts to avoid infective stages and compensate for the pathological effects of infection. Now, we're going to talk about how nematodes drive their hosts to limit the number of parasites that establish. They can do this through their immune response. Now, the immune system is super complicated. It does all kinds of different things. But I want to focus on one example that really shows how the host's immune response can limit the number of parasites that can establish. It comes from a science paper from 2005 that was done on mice and the whipworm, Trichuris trichiura, which can infect humans as well as mice. This nematode species is one of the geohelminths, an intestinal parasite. Briefly, this nematode burrows its teeny tiny head into the intestinal epithelium, and from there it sucks lots of blood, basically tapping into the capillary system that serves the intestinal tract. Here is the favorite habitat of Trichuris trichiura, the intestinal epithelium, or the internal lining of the intestine. You'll remember that in the vertebrate gut, the intestinal epithelium has all these tiny folds in it. Little microvilli increase the surface area for absorption that the animal uses to absorb food. This is a cross-section of the intestinal epithelium of a mouse. The base of the crypts is the solid tissue of the intestine, and then the cecal lumen is the interior of the intestinal tract. So the upper part would be where poop and food are flowing through the intestinal tract. As the intestinal epithelium renews itself, it basically pushes cells from the base of these crypts up to the surface where the little microvilli touch the intestinal lumen and the material that's being passed through that intestinal lumen. The stem cells that create those new cells are at the base of these crypts, and you can see that the newest cells are in the cell positions 0 to 10. Then the medium-aged cells are 11 to 20, and the oldest cells, those that are about to die and be sloughed off, are in positions 21 to 30. And once they get to the intestinal lumen, the cells die, they get dumped into the tide of poop flowing down the intestine, and then they're replaced by the new cells that are coming in behind them. This is just the normal process of how the epithelium renews itself. Now, in some mice that have a trait for resistance against this parasite, the arrival of Trichuris trichiura in the intestine is recognized by the immune system, which then speeds this process of cell replacement up. This is sometimes called the epithelial escalator. Think of it as an escalator of death for parasites. Resistant hosts can make the escalator go faster, rapidly sending the baby parasites over the edge and ejecting them before they can establish themselves. Susceptible hosts can't increase the speed of the escalator fast enough to eject those baby parasites, which means they're going to have to live with those worms for the rest of their lives. For a long time, scientists knew there was a strain of mice that was resistant to Trichuris trichiura, but they didn't know why. You could do experimental infections of the resistant and susceptible strains of mice. Here, the resistant mice are in white, and the susceptible mice are shown in black. By day 21, after you experimentally infect your mice, the resistant mice are worm-free. They have somehow killed all of the parasites that were put inside of them by the experimenter. But the susceptible mice never get rid of those worms. How do the resistant mice do it? Well, it turns out that resistant mice can turn up the speed of the epithelial escalator and make it go much, much faster than susceptible mice can. In this plot, we're looking at resistant mice in white and susceptible mice in black. On the x-axis is time, day 0 before the mice are exposed, and then day 14 after exposure, day 21, day 35. On the y-axis is the number of cell positions moved per every 10 hours. Track the columns for the resistant mice in white first. Things are slow before exposure, but as soon as they've been exposed, that escalator starts roaring and stays roaring until all the worms have been cleared. Now track the columns for the susceptible mice in black. Things are slow before exposure, and then even 2 weeks after exposure, they're still slow. The escalator doesn't kick into gear until day 21, and by then it's too little and too late. The worms are all established. The susceptible mice have missed their chance, and now they have worms forever. This is a system ripe for red queen dynamics, a system where we might expect to see a co-evolutionary arms race. Imagine when this resistant phenotype first arose in a mouse population. By day 14, that escalator is humming and kicking out those new baby whipworms. This would set up really strong selection for any whipworm that could mature faster than that, which of course would set up strong selection for a faster epithelial escalator in the host, and so on forever. As a mouse, it takes all the running you can do to keep the same burden of worms. If you want to have fewer worms, you must run at least twice as fast as that. Host and parasite are locked in an eternal battle, where the host is trying to clear the parasite and the parasite is trying to make more of itself in the host. So far, the nematodes have taught us a lot. We've talked about how hosts can avoid infective stages by migration, they can compensate for pathological effects by making hay while the sun is shining, and they can limit the number of parasites that establish. In the next video, we'll talk a little bit about what the nematodes have taught us about sexual selection. I'll see you in the next video.